Just confirm if my screen is visible. Is it visible?
Yes, sir.
Okay. So, let me start. So today's topic is it's from your unit 3, building time series models and performance evaluation using different this time series techniques. Maybe it's ARIMA, SARIMA. There are many more. Okay. So we will touch upon this ARIMA and SARIMA, and we will see how this time series model will help you to predict. Okay, because ultimately for these time series models, one of the component is time. Okay, and how we are going to predict it. Okay, so one of the X component is time, and your Y is obviously the values, corresponding values. So we will try to see how ARIMA and SARIMA is going to help us predicting the time series model. Okay. So typically you'll see how in economics, the GDP, inflation, these kind of stuff, you are trying to see how they are related. Okay. So let's say if GDP and inflation, so they are also time dependent. Okay. So we will see through different examples, and we will try to implement it. But GDP and inflation, if you have studied this economics, there is one classical case that is called Phillips curve. So if your GDP is growing, maybe it is related with inflation, and inflation is related with unemployment. Okay, the more inflation and unemployment is going to decrease. So this is some curves. Okay, so the first one is ARIMA, and sometimes we call it ARIMA also. So don't get confused with the sounds and all. So ARIMA is a general class of this models, stats model for time series analysis for forecasting. Okay, it stands for autoregressive integrated moving average. Okay, so autoregressive and integrated moving average, you are trying to add the moving average, and they are just a kind of regression they use, autoregressive. Okay, so when applying these ARIMA models, you use a time series past values and forecast errors to predict its future values. Okay, so obviously for any machine learning models, we have to depend on the past values. So past values is nothing but whatever we have the historical data, and based on historical data we put in to the systems once we build any time series models, and then we try to predict through the unseen data, which is typically called a test data. Okay, that is why it is saying errors to predict its future value. Okay, obviously there are some errors. So when you see the actual and predicted value, you will see there is a difference, the difference of the errors, and minimizing the error is how you are going to evaluate how our models are working once you apply this ARIMA model. Okay, so if you see the background of this ARIMA model, so before looking at the details of ARIMA model, just we have to define this time series. Okay, so the time series is sequence of data points collected in a time order based on the time series characteristics. We can divide them into different categories such as univariate, multivariate, linear versus non-linear. Okay, so for example, univariate means we have only one variable, independent variable, but multivariate means you have multiple independent variable. And you know that what is linear and non-linear. Okay, so we will only look at the time time series that are univariate, that is they only deal with the one variable, linear and non-seasonal. Okay, so in ARIMA you will see the only one variable and try to see how they are going to predict it. Okay, So before building ARIMA models, we should check whether the time series is stationary. Okay, so we have to check whether your your model is stationary or not. Okay, so on the right side, if you see here, so this is a stationary time series. Okay, and this one is oscillating. Okay, so this one is a non-stationary one. Okay, because it is oscillating and their values are different, but here their magnitude is different, but they are oscillating on the same, you can say, the time intervals. Okay, maybe their values are same, but their time interval is different, but values are same. Here values are different, even the time duration is different. That is why it is non-stationary. The magnitude is different, but here they have the same magnitude, but time is different. So that is why this is stationary. Okay. So we will see how we are going to implement ARIMA. Okay, so some of the example of this time series is, for example, tracking daily, hourly, weekly weather data. This tracking logs and some of the economic indicators. If you are tracking the annual unemployment rate over the period of 10 years, maybe if you have, let's say, 50 years of a record for any country, then you can see how your unemployment rate has performed. And monthly bike sales, you can also check daily stock prices. Okay, so these are some examples you can deal with this time series. And the components, so there is something called the cyclic component, seasonal pattern. So if you see this one, first see this seasonal one. So in seasonal one, you will see there is some peaks here. Okay, and there is a valley here. So it at certain time period, it show you the same kind of patterns. Okay, so just give me a minute to 1 minute. Just give me a minute. Okay, and then I'm coming. Just give me a minute. Okay, so if you see this component, the seasonal one, there is a the valley and peak. Okay, and the trend, if you see the trend, Trend means there are certain same patterns. If you see this one, this pattern and this pattern is same, and this one is cyclic. Okay, so these are the some the patterns in the data, and there is some trend with seasonal patterns, so their magnitude is different. Okay, so 1 minute. So this is same thing, and I have already shown you this one, this time series forecasting. This one is a historical data, and this is your forecasted values. Okay, so this is some examples. Okay, and time series methods and models. So the methods are, let's say, one is univariate if you have only one independent variable, and multivariate, for example, if you have multiple independent values. And the models, for example, if you have let's say if some moving average values, this LSTM is your deep learning techniques, the ARC and WARE. These are also some of the techniques. Okay, so we will see this ARIMA first. So ARC and WARE is using some of the this time series methods, but LSTM and ARIMA and SARIMA, majority of the enterprises they use this one. Okay, but LSTM is deep learning techniques, that is long short-term memory. So they are using this a technique called deep learning. They use the deep learning techniques to understand the further hidden patterns. If your ARIMA is not giving a best result, you can switch on to this LSTM. Okay, if your data set is huge, time series huge data, because for deep learning, if you have a huge set of data, then only you just need to perform this LSTM. Okay, so for ARIMA model, so I'm not going into the detail of this technical detail of ARIMA, because ultimately you have to just understand few things here. For example, if this YT is a prediction, okay, just see this one, and the alpha is a constant and linear combination of lags of Y, beta 1, beta 2 up to here. Okay, these are the some linear combinations of Y. Okay, and this theta is a linear combination of errors. Okay, so when you combine it, you get a time series, the equations. So this is how you have to apply this ARIMA model. Okay, and there is one method called differentiating I. So I will show you through this Python programming. So just see in the ARIMA there is some process. Okay, so you have to convert the time series object. First you have let's say if you have a data, then you have to convert it. This is a data pre-processing, and there is something called ADF test. So through Python I will show you what is this ADF test, if data is stationary or not, just to check. If it is stationary, then you have to just increment the D. Okay, and then there is some differences. Let's say if you have increases it, if it is already stationary, then we have to check, we have to find D, P and Q. There are the three factors in the ARIMA model: D, P and Q, and this will give you this forecast future values. Okay, so in ARIMA, PAC and ACA value is important. Okay, and this difference. So let's see. So for ARIMA, this P, D and Q, as I already told you, the P is the number of autoregressive terms, how many terms which are autoregressive, which is denoted by P, and D is the number of non-seasonal differences, and Q is the number of lagged forecast errors. So when you add it up, it will give you this prediction equations. Okay, so 1 minute. And for this test P, Q and D, so when I run this Python programming, then you will understand this ADF test and all these things. So I'll come back to this slide. Let me show you this Python first, because you will not understand all these things. Just remember that P, D and Q, that is important in this ARIMA model. So once I run it, the Python programming, then you will understand. So let me just quickly run it. So data set is here, okay, in the passenger data set. So once you run it, so this is monthly data and their passengers. Okay, this ADF test. So once you run it, this ADF test, the value is 0.09, the P value. If P value is more than 0.05, it means our null hypothesis will be rejected. So what is null hypothesis? It means the number of passengers are, let's say, are significant. Okay, or you can say there are, let's say, certain number of passengers. That is your null hypothesis. Alternate is that it's not. Okay, so you have to reject the null hypothesis, and whenever you start any time series model, you have to check this hypothesis testing using this ADF test. Okay, so okay, so our null hypothesis is our time series model is not stationary. It means it is stationary. So okay, so our model is, let's say, time series model, the passengers you can say, or you can say the model which you are trying to predict the number of passengers. So they are stationary. That is our null hypothesis. Alternate is it is not. Okay, so as it is saying, it is the value is more than 0.05, that is we are rejecting null hypothesis. It means our data points are non-stationary. Okay, so this we have to assume in every single time series model, this stationary part and non-stationary part. Okay, I was just missing out this point. Okay, and the value is more than 0.05. So ADF test will give you this P value. Okay, and when you run it, you will see it is non-stationary. Okay, because it is non-stationary. Had it been stationary, it would have like this. Okay, not upward trend. Okay, so here now we are plotting the data and we are trying to check let's say the original series, the data, how our data is. As you can see, our data has upward trend, and once you have run it, this original series, just see, this is just plotting of the data points. If you see up to this, our data point is this upward trend. It means non-stationary. But this one we are just introducing a D, that is a differencing. Okay, first order differencing. So once we introduce this first order differencing, you can see we are just trying to make it a stationary. Okay, so it has come like a horizontal way. Okay, and then we have introduced the second difference. So now it is like a stationary. So When your time series is non-stationary, this one is a non-stationary, we have to make it stationary. Okay, stationary means you have to keep hold of the magnitude value. Time will fluctuate, but the magnitude, it means if you starting with the 400, it should like this. Okay, it should not be like this because magnitude is different. Time is also different and magnitude is also different, but in stationary magnitude will be same, time will be different. Okay, that is why we are making our time series model stationary. That is why we are introducing first differencing, second differencing, and if it will not be like a stationary one, you will also introduce third differencing also. Okay, to make it a stationary. And until then, okay, then this comes, then we are just trying to plot how it's autocorrelations, how values are autocorrelated, and this is the same. You can see one thing, if you see here, we can see how time series has become stationary. Now in our case, our time series model is stationary now, and first order differencing, few noises were introduced. This is just talking about the above plot. Now you can check this stationary part using this autocorrelation plot. Okay, so if you see these autocorrelations here, the noise is reduced here. Okay, but if you see the thickness here in the first plot, it is more. It means the data was non-stationary, but if you see this one, the thickness is less, autocorrelation will is less. It means now it is the data is your time series model is stationary now. Okay, this autocorrelation part will show you this. Now, okay, we have to run this. Now, there is something called this partial autocorrelation, which is just repetition of, just to check whether your data points are stationary or not. Okay, so this is just a repetition, partial autocorrelation. Okay, if the values are, how your values are correlated. Okay, now come to see how the P and D values. Okay, where is the, okay, now coming to this ARIMA part, just see this ARIMA part once, 1 minute. Okay, now just see this one, this ARIMA part. The order is 1, 1 and T 2. Okay, this P, Q and D. Okay, so the difference, okay, and this thing, this sometime you have to check it through the manually. Okay, okay, so manually we have selected P, D and Q. Okay, you can also increase the order just to check, and P, D, Q, these are also coming from autocorrelation and that this plot. Okay, so once you fit in the model, this ARIMA is a function. Okay, and data.passengers is just we are plotting the passengers. Okay, so how this ARIMA model is giving us the result, this one, this is ARIMA model. Okay, so the order, if you see the order PDQ, the ARIMA model we have applied, the AIC and BIC values is almost same. Okay, and the sample was, the starting sample was from 1949 to 1960, which is ending point, and these are the sum coefficient like a regression. So as I already told you, this ARIMA works like a regression, auto-regressive. Okay, some standard errors are here. Okay, and the P value at 25% of significance, 75 or something like that, 5%, 95%. Okay, 5%, 10%, 1% significance, and these are the sum of the different tests. Okay, just you can Google it out, and if you see that there is Jarvie test, probability or something. Okay, there is a skewness, means how your data is distributed, whether it is left is skewed or right is skewed, kurtosis. These are some of the data description kind of a thing. Okay, just to check how your time series model, how data points are distributed, and you can have a clue that okay, how many outliers are also there. So skewness and kurtosis will also give you a clue that how many passengers are outliers, how many passengers, you can say how many data points are above the mean or below the mean. So this can give you the clue. That is why this all are very much important to understand. They give you certain informations, okay, which are critical to the model. Okay, now coming to this SARIMA part, for that SARIMA you require some libraries. Just let me check what kind of library you require. This PMD ARIMA, this library you have to install, okay, and if you install this one, this will take some time. So once you run this one, pip install this, and this is auto-regressive, auto-regressive, because once you apply this auto-regressive, and this is our data where our passengers information is there, okay. So this auto-regressive, this auto-ARIMA will find the PDQ values, this one 1, 1 and 4, okay. It will find it by self, okay, 1, 1, 4. And once you run this auto-ARIMA.summary, this will give you this SARIMA part, okay. This is a seasonal auto-regressive, seasonally auto-regressive, okay. And this is quite similar to this ARIMA. If you want to find some signal component, if you want to capture some signal component, then you have to use this SARIMA, okay. And we have certain information, AIC, BIC, likelihood, the model, how many observations are there, the variable, your dependent variable is Y, okay, here, and some coefficients. These are some, the time series components, and their coefficients. Had it been significant, it would have some star marks. Star marks are not here, okay. If you go here, you have some skewness, kurtosis, probability, Jarque-Bera test. This is for test for, if your data is, let's say, how your data is distributed, whether it is stationary or not, and sometimes it is just a check of whether your data is following normal distribution or not, something like that, okay. And one of the good component is heteroscedasticity, and this is one of the features of regression also, okay. Homoscedasticity and heteroscedasticity, okay. So if you have to know more about this, just Google it out, because heteroscedasticity and homoscedasticity are typically, people in economics, they try to use it because there is one more subject called this econometrics, okay. So people using this econometric subject, who are studying this econometric subject, they can have an idea of this homoscedasticity and heteroscedasticity, okay. So this is ARIMA and SARIMA. You can have a look. So if you see this Python, I'm just quickly running it. So this is data point. ADF test is just for this hypothesis testing. First you will assume that your data points are stationary, and null hypothesis, alternate is not stationary, and the p-value is more than 0.05, so you have to reject the null hypothesis, okay. So now if you plot the the data points, you will see it is non-stationary. So for any time series, if your data points, your time series data are non-stationary, you have to make it stationary. So for a stationary, your magnitude must be same, and the time component will vary, okay. So you are just putting a differential, first order differentiating, second order differentiating, till it becomes a stationary. So if you see, this is like a stationary one. The values are little bit varying, but the magnitude is same, okay, here. So we have to bring third order, fourth order, till it becomes a stationary, okay. Then autoregressive is just a cross check of whether it is stationary or not. Just thickness has reduced, okay, here. And this partial correlation also just similar to this this autoregression, okay. It's nothing important. And then finding P, Q and D values, okay. So if you see this difference, this part diff, this difference part, this will give you how much p, d and q values we must have. Okay, but the value q typically we choose is 2, which is by default. Okay, and this is our the ARIMA part 1, 1 and 2 here, p, d and q values. If you see this order, okay, the order of ARIMA. So this gives you the summary of ARIMA and SARIMA. So one that one thing which you can notice is AIC value that needs to be lower while performing the ARIMA model. So if your AIC value is low, you have to make this AIC value low, because if you see the BIC is more, but ultimate game is to make this AIC value lower. Okay, that you have to take care of. Okay, so you can reduce this term by changing the value of q parameter. So the q is depending on the AIC value. If you will this modulate the key value, then you are able to reduce this AIC value. Okay, which is important, and the business persons try to see the AIC and BIC value when you see the time series, the results. Okay, this is more critical one. And this is SARIMA. I will see what is SARIMA here. This is a seasonal ARIMA, extension of ARIMA that explicitly supports univariate time series data with a seasonal component. Okay, it adds 3 hyperparameters to identify the auto regression. One is A, differencing D, and the moving average. Okay, for the seasonal component for the series. So if your data points are following some seasonal patterns, and if you want to introduce the seasonal patterns also, okay, so in that case it's important to use this SARIMA. Okay, so if you see this P, D and Q, okay, they are saying they have used a word called hyperparameters. Okay, so this for time series model or SARIMA models or ARIMA model, the hyperparameters are P, D and Q. Means they are fine-tuning the models. If you increase D, P or Q or any one, if you know which one to increase, okay, just to increase the performance of time series model, that is where this is called hyperparameter, because hyperparameters are typically which are learned from the model. Okay, so model learning from the the data sets, they learn what should be the the P, D and Q. So that is called hyperparameters. Okay, and sometimes it is also external. People put, for example, if you want to put Q equal to 3 or 4, and you want to check whether your time series model is stationary or not, and whether they are reducing AIC values or not, so they will also fall under this hyperparameter. So every single machine learning algorithms have hyperparameters. Okay, so when I teach you this logistic regression or random forest, I'll try picking up these hyperparameters, because if you want to increase the accuracy of any machine learning models, we typically go and to check the hyperparameters of the models and try to fine tune it so that it gives you some the accuracy higher. Okay, so that is important. Okay, so some of the applications of this time series, if you see this time series, I think I have used this slide earlier also. So the important is here time series, this economic forecasting. Okay, so majority of the time series model fits into this economic forecasting. Marketing and sales forecasting is the people in the marketing, they also use this time series models. Financial analysis. Okay, so these are the few fields where you will find it they are using widely. Okay, and these are the rest of the the applications which uses this time series analysis. So there is one more topic today, so just let me quickly pull out the slide first. 1 2 is lecture 14. Yeah. So I'll upload this time series coding and then try you running it. Okay, spurious of this regression. Sometimes we call it a spurious or spurious or something. So just check in the Google how you can pronounce it. But we call it here spurious regressions. So spurious regression means it's like we call it in Hindi. It's like a fake or jali kind of stuff. So you might have seen, the fake currency, the fake drugs. It's like a jali notes, okay, jali medicines or something like that, okay. So we will try to touch upon this spurious regression and pair trading interest rate or something, and we will try implementing using Python. So our focus would be on this spurious regression. So we all know what is regression. So so in regression we have a dependent and independent variables, okay. So for example, let's say sales and revenue. So once you increase the sales, obviously revenue will increase in that proportion. So obviously if you are not giving much of the discounts and all, okay. So in that case it is related. For example, if you increase one, another will also increase in some amount, okay. So for example, so if there is no causal relationship between the two independent variables, so in that case we say it's a spurious regression, because they are false regression. They give you the false result. So through one example we will see what is a spurious regression, because it's just a theory, and the people who are modeling this regression kind of stuff, if they are finding some independent variable which are independent and giving you the vague results, okay. So how we are going to fix it out and how we are going to figure it out, it's a spurious regression, okay. That is more important, okay. So here if two variables are, they don't have a causal relationship, so this gives us a red flag that okay, it will show us some spurious regression. So just see, this is one of the code. We have y and x, that is two independent variables, and this ey is exponential of y, e to the power y and e to the power x, and this is a random number. So we are just generating a random numbers here. So and then we are applying this in this is our command, so don't get confused. Y tilde x is a relationship, okay. This tilde sign is a relationship. It is like y equal to x, okay. Output equal to, because we have only one independent variable, okay. So once you run it, they give you certain intercept and all, okay. The coefficients, the intercept, the x value, because we have only one independent variable. Had it been two, we would have got one more independent variable, and this is star marks means it is the value is less than 0.05. that is why you got a star marks here. So if you see the estimated coefficient of this x is 0.31607. The coefficient of x, this coefficient of x, if you see, coefficient of x is 0.31607, okay. And and it is significant because the star mark is here. Despite that, the true coefficient is 0. If you see, their true coefficient is 0. This result mistakenly indicate that the y and x are related. Actually, they are independent of each other. But if you go on to investigate their true coefficient, the true coefficient is 0. Okay. But here you will see everything is perfect. But it's an example of a spurious regression. They are independent of each other. They are not putting any, a kind of, you can say, the causal effect. One y is not causing anything on x, and also x is not causing on y. Means two variables are going in two different directions. Okay, that is why it is a spurious. It's a fake. Okay. And through Python, just see how we can implement through Python. So here in the spurious regression, just see, we have some libraries like in linear regression. I have shown you. It's similar to linear regression. So let me run it and let me explain you. Okay. So here, these are some libraries, a similar one, and we are creating two random variables which are not related, up to 100 data points, two random variable which is x and y. Okay, and we are adding a third variable that affects both variables, that is a z. Okay, z is 10 of coefficient of x is 10 and coefficient of y is 5, and we are adding this random numbers, okay, to both x and y, and we are creating a third variable z which is affecting x and y too, but x and y are independent of each other. Okay, and now we are just plotting x comma y. This is like a scatter plot, and x and y, and this is on the x-axis the value of x will lie, and on the y-axis value of y will lie, and we are plotting how it looks like. A scatter plot means it gives you a dot points. Okay, so if you see these values, this is giving us the y and x value, x and y values, and if you see the values are very much scattered. Okay, and when you are running a linear regression and trying to find out the r squared value, because every single regression will give you r squared value, so we are finding y on x, what is effect of y on x, and what is effect of y on z. Okay, so once you see the regression, the r square value is 2.12 something, and r square here is 0.243. Okay, so through regression, so y on x, the r square value is this one. Okay, so just see what this analysis is going to tell you. So the r squared value for y on x and y on z, the r square value is 0.015. okay, and here is 0.219. so here I think the value is different. Okay, yeah, so it generates the variable x and y that are not related, generates a random number. We can create a third variable z, that is a linear combination of x and y. We have already seen z equal to 10 of x plus 5 of y plus some random numbers, that is some random noise which we have added. So random noise is nothing, it's this one. We are adding a noise to z using x and y, which is a random number, and adding some noise. Okay, so once we plot the relationship between x and y, which shows no apparent relationship because it is scattered, the values are scattered. If you draw a line, you will not find much of the relationship. However, once you run a linear regression of y on x, you get r square value of 0.08, indicating a very weak but statistically significant that this is a spurious regression since y and x are not related. Okay, the value of r is so less. Had it been 0.5, it would have shown some kind of a relationship, but it is so less. Similarly, if you see y on z, you get a squared value of 0.96 because it is a random variable. So the value, when you run it, you will get a different value. Every single person will get a different values because the random number which the system is going to generate for you, it will be different for every single person. So the value may different from the slides. Okay, so once you run a linear regression y on z, you get a z square value of 0.96. so now we have a strong relationship because the value is more than, it's up to 100%, means the relationship of y on z means the value have some effect on z. Okay, so this is a correct regression. Okay, so it means if your value is so low, r square value, it means it has some spurious regression. Spurious regression means the variables are totally independent and they don't have any effect on your y. So it's important that you just remove that variable. Okay, so spurious regression will give you this kind of information. Okay, and there's something called pairs trading, which is related with your this trade, and all the people who are well versed in this trading, they can understand this pairs trading. So if you see this one, what are the important ideas of this pair trading? On the right side, if you see the entry, exit, or something like that. So it's like you know how your this stock, how they are performing and what is their trend. So entry and exit will give you the trends, because it's higher, it's opening at a higher end but dropping it to these values. Okay, so two stocks that move similar to each other, how two stocks are moving in the the same direction maybe, or different direction. For example, PNR and SWK, it's a two stock. So find where their spread diverges from its historical mean. If you see how the stocks are diverging, means how they are moving away from each other. So this will calculated through this something called a spread, how spread the values are from each other. Okay, so sort the overvalued stock by the undervalued stock, and exit reverse the trade when the spread converges and pocket a profit. So the people who are in this stock market, they can understand these terms, but visually just you just know what is this pay as stat, because it's just more of economic terms. So but mathematically how you can see how they are implemented it. Okay, so spread, as I already told you, if there are two stocks, stock A and stock B, so how a spread can be defined through, you have to take log of a stock A and you have to divide by number n. This is hedge ratio. So it's a hedge ratio is people it's typically in the finance they use this hedge ratio, which I can recall now. So hedge ratio, and then you have to take log of stock B. So this will give you the spread, means this will give you how a kind of you can say the opening and closing, or the how wide to stock is. So people who can trade in this stock and all, they can understand this one. And the important part which just I want to highlight in this pairs trading is this one. Principal component analysis and k-means clustering are used to find potential candidates for pairs trading. This clustering exercise finds the stocks that trade similar to each other. For example, if you have, let's say, 20 stocks, okay, and now people who invest in the stock and all, they just want to find out the similar stocks, as it is unsupervised learning kind of stuff. So obviously you have to use this principal component analysis or k-means clustering, because the similar kind of stocks performing, the similar kind of stocks which are performing in the same way can be clustered, can be put in the same bucket. So the PCA and k-means clustering can help you out with that. Okay, and then there is something called co-integration stuff. Measure whether the spread between the two stock is stationary or not. So if two stocks are stationary, for example, the magnitude is same but they are moving the same direction, so you don't like those stationary the stocks, it must perform, right? So these are the two, you can say, the important thing which are critical with this pairs trading, that is related with the stock. So if you have to find out the similar stocks which are performing, then you have to apply these two unsupervised learning techniques, that is PCA and k-means clustering. Okay, these two are going to give you a bucket where you can put the stocks which are performing in the same way, okay, in a similar fashion. Okay, so this is your pairs trading. So I'll upload all your PPT and then you can have a look. Okay, so